Before I start my talk, can I do a quick survey? How many of you are students? How many of you are electrical engineers? Okay, a lot of electrical engineers. Oh, yeah. How many are computer engineers? Okay. I see some overlap there. Can't get away from that these days, can you? No. How many of you would regard yourselves as analog engineers? Okay, well, you're in the right place. That's for sure. So how many here have used Spice before? Okay, a little bit. Okay. How many of you have used LTSpice before? Well, sometimes get some idea. The younger people.
Letters where they were from LTSpice to LTSpice. That's the gap.
Oh, I see. Right. Well, there was Spice, of course, originally. And then there was Spice and.
I may have used Spice before they called it Spice.
Oh, really? Really?
Before 1.0.
It was some kind of.
It was. I'm not sure what I was using, but then later said, "Oh, that's Spice." And I was really.
Yeah, I understand it was a program that was developed by University of California, Berkeley, to evaluate whether circuits would survive nuclear attacks. And it was called something else then, altogether. Some really weird, awful acronym, by the way. Anyway.
Is that the last version of LTSpice? Because I know QSpice is pretty popular as well. We got the group LTSpice now, right? Works in core mode.
Right.
QSpice. I'm wondering, is that the last iteration of LTSpice? And do you see it dying?
Well, you're talking about Michael Egelhart.
Yes.
And he is certainly working hard at Corvo now, which is a interesting recent merger of two IC companies that have done a lot in the way of very high-speed electronics, a lot of military applications. And he's carrying on the work he did with linear tech and with analog devices and so on. He's carrying it on. He's doing an amazing job. It's a version of Spice to watch. There's no question about that. The QSpice, especially because it incorporates the ability to actually include C programs in the Spice simulation. C programs and Verilog, hardware description language programs can actually be incorporated in the Corvo system, and it's free too, by the way. But so my name is David Fiore, by the way. My biggest credential here today is that I've been building electronic circuits for something like 50 years, and I work with from everything from vacuum tubes to discrete bipolar transistors, and now with integrated circuits of all kinds. And I've been working with LTSpice more or less, or with Spice more or less, when it's since about 1990. So I've done a lot of simulations over the years. But what is LTSpice? Let me answer the question. What is LTSpice? And it's one version of Spice. And Spice is a simulation program with integrated circuit emphasis. The idea is to simulate circuits before you build them, because when you build an integrated circuit, it can take a very long time. It was not unusual in the day for it to take a year from the time you decide to build a chip to actually getting your hands on the actual circuit. So you want to make sure that you don't make any mistakes. And in the day, I have to say, it was Spices were slow, computers were slow. It was getting models wasn't an easy thing to do like it is now. A lot of things have improved since then. Although the program is for integrated circuit engineering, our emphasis for engineering integrated circuits, because it's so much easier now so much quicker now with fast computers, with the internet, it makes models for every kind of IC and every kind of component are readily available. These things are, it's much easier now to apply it, even to the things we do every day. And so that's, just want to make a point here about what I'm doing. I don't think I'm not trying to teach anyone LTSpice, and it's a good thing I'm not, because a lot of people have some idea what Spice is about. But I'd like to just show you what kinds of things you can do with it, the scope of what it can help you do, how it can help you get your products or your designs working faster or avoid making big mistakes. That's I think it's interesting that Spice was an open source program developed by students at the University of California, Berkeley, way back in 1973. That's like 52 years ago. And that the heart of all the Spice programs, LTSpice, QSpice, is followed from that work and have remained, for a large part, unchanged. A lot of the specification, a lot of the language elements are the same, even now. But it's stood this test of time, and there's lots of models around, and we use it a lot. So here are some of the fundamental components in Spice. If you don't know what these things are, you're probably in the wrong room. Okay. But then again, if you know what these things are, Spice can actually help you solve lots of equations using lots of differentials and integrals. And these are kinds of things that are necessary. Calculations involving these kinds of equations are necessary to emulate electronic circuits. And so anything that actually uses differential equations could be applied to LTSpice. You can actually use LTSpice to do a lot of things outside of electronics. We can go to you can use it to simulate mechanical systems. You just have to make the corresponding substitutions, mass for inductance and spring constant for something related to capacitance. And if you make all these substitutions, you can actually apply LTSpice to mechanical systems and make sure for example, your remote controlled car isn't bouncing too much. And you can actually make graphs of what kind of bounce to expect from what kind of hitting what kind of obstacle on the road. But you could actually use LTSpice to model suspension systems. You can also use LTSpice to model thermal systems. So it's all a matter of just substituting for the differential equations that are involved in electronics for the differential equations involved in the other fields. But it's useful. It's got a nice graphical user interface. It's fast. And so it's got a lot of positive. But even beyond linear transient behavior and differential equations, linear differential equations, Spice has a lot of capability in the way of arbitrary functions. You can make any function at all, just about, and just embed it in a what they call a arbitrary behavioral source, either voltage or current. And just to give you some idea, these are all the functions that can be embedded and combined and together to make arbitrary functions in LTSpice. So you can pretty much put any kind of complicated calculus equation into a Spice model. You can actually use it as a calculator for calculus. But that being said, but what is LTSpice not good for? Well, one thing I've dealt with lately, power magnetic components. Problem is, power magnetic components have a effect called hysteresis, and they have memory. If they didn't have memory, magnetic materials couldn't be used as magnets. Some of the magnetization is remembered, but in electronics it's a problem because the components can get stuck in saturation and then they don't work properly. Anyway, it's very hard to model that because it involves memory in the part itself. part itself remembers its history, and then that becomes problematic. Can be done, but it takes a lot of work. It's just not practical. Except for transmission lines, modeling inductors and resistors, you have to make distributed models by just stringing together a bunch of smaller resistors or smaller capacitors. If you're doing a resistor capacitance distributed network. So it's not the best for that. Probably if you need it. And I have to say, it's not good for fine art. Although you can make the Seju figures with LTSpice, you can actually make these drawings if you want. So that can be interesting if you have nothing else to do. But one thing it's definitely not good for is modeling this kind of thing. Actually, I think this was the product of someone who didn't use LTSpice, whose circuit failed and had nothing better to do with all the components and PC boards he made. So we want to use LTSpice to avoid wasting the parts. Acquiring LTSpice, it's free, which is one of the reasons it's so popular now. It came originally from Analog Devices. It was the brainchild of a fellow named Michael Angelhart, a software engineer there at Analog Devices at Linear Technology. Linear Technology was more or less recently acquired by Analog Devices, and they also acquired the LTSpice. But it's all there to help people, encourage people to use the products manufactured by these companies. It's easy. There's lots of links you can get to real quick. I just did it there. But there's more than one way to get there. There's a nice Wikipedia page even on LTSpice. So if you forget everything else, you can always go to Wikipedia and type in LTSpice and learn everything you need to know. Here's I was going to show a little example of actually doing that. And I think I can.
Today, let me show you a studio
Here. Let's see. How do I? Okay. No, I'm afraid I'm not familiar with this computer here. How do I speed up the actual video? How can I actually fast forward? Okay, that wasn't the right thing to do, was it? Okay. This. Ah, there. That's going to be a problem. Okay. My version of PowerPoint lets me move ahead and select parts in the screen here. I can't seem to figure out how to do that right now. Oh well, okay. Anyway, one of the first things I did as a young boy, I was interested in audio, and I was interested, and someone gave me a pair of headphones, but I had nothing to plug it into. So I thought, let me make a little headphone amplifier. Now I want to show this because it illustrates some of the features of LTSpice that can be really handy if you're trying to build a circuit like a headphone amplifier. So I have two questions here. Should I build something with discrete transistors, or should I use an inexpensive integrated circuit? Let me look at that and see what the differences might be. Here's all spec sheets for discrete transistors. And then this is the power transistor, an old power transistor there. Okay. It's got a bandwidth of 10 kilohertz, if you can imagine that. It's still available, but it's a very, very slow part. It's a part I actually used when I was a boy, by the way. So here's a, I can do this quickly. Now I wanted to be able to fast forward on this. I can't figure out how to do it. Is that up here? Okay. Anyway, you put it together, and I really want to get to the end of this because we don't have a lot of time. Here. Yeah. Just move ahead of it. So the main benefit of next screen. Well, anyway, that one takes too long to get through it. But let's look at the LM386. Now that's a single chip. It's been around for a long time. It's got like 12 or 13 transistors inside. It's got 12 or 13 transistors inside it. In the data book, it gives you a schematic. So I wanted to build that schematic. Here we go. So simple enough. So I did. Yeah. So it's not too hard to do. Laying parts down. Use a little economy of scale here. Let's put down the components first. Do the wiring between them. Put the labels on them. Put the labels on. Last. Look at the schematic. Let's simulate it. Let's look at the output signal. Oh, I made a mistake. I forgot to specify a sine wave input. So I'm doing that real quick here. So you would say, you'd have to ask, why would you bother building a simple circuit like that in a simulator like LTSpice when it's only a few parts with a soldering iron, with any facility with a soldering iron, you could probably build that in 10 minutes. Well, the problem is you don't really know what you've built when you build it. If you want to know what the distortion is, you have to get a distortion analyzer somewhere and hook that up and figure out how to use it. And but with this, I just showed the screen. With this, wish I could figure out how to get back on that. How to go back. But with this, you can instruct with the for command here, you can instruct LTSpice to do a Fourier analysis on the signal and then sum up the contributions of each of the different harmonic distortion frequencies and come up with a total harmonic distortion for it. So you could find out in advance of building the circuit what the harmonic distortion of the of it is. And it's a lot easier to do that this way than to find an instrument and hook it up and tweak it and figure out what the answers are. So here I'm showing how the part responds to different levels of input. I also show how it's, then I measure the distortion again at the end with overloaded input, but that's all well nice. Now, so instead of having to build it and then find instrumentation to do it, we can, okay. Now I wanted to show how LTSpice could be used to understand something like, well, the interface of analog signals between devices. And it's a, I don't think we're going to have time for it. I may not have time for it, especially since I can't figure out how to fast forward my recordings. But I don't know if any of you have any interest in car stereo, but car stereo analog interfaces in car stereo. Aftermarket car stereos have a problem with noise getting into the signals, and here I'm using LTSpice to show how the noises get into the signals. And then I was going to show a couple of different solutions for noise. An audio isolation transformer, one way to get around noise problems in analog interfaces, and we could show how that could have shown how that can model that. But of course, I can't really do that in a time-effective way right now. Okay, so anyway, I was going to show. Here's the model with an isolation transformer, and if we followed that through, we could easily see that its low frequency response is not very good. This is an actual professional audio isolation transformer. It does not have good low frequency response. It's very hard to make a good isolation transformer with very low frequency response. So they tend to be expensive. They're bulky, and it's probably a good idea to try to avoid them if you can. So a lot of equipment makers instead use a okay, what's wrong here? It's skipping too much. Okay, so I've developed a device to help cancel noise pickup in cables, interference pickup, and I was going to show the LTSpice for that, but here's just taking the transformer interface and showing my synthesized transformer. And it's a little more complicated, but if we had time to go through this whole thing, I would. You could see how well it performs. It actually performs better than the transformer isolation. The isolation transformer. It's got absolutely flat frequency response. It's got better isolation actually, and here I'm showing the different. Looking at the noises, I was looking at the noises that I was introducing into the signal path, how they add up, and then, boy, I wish you know what? I think I was using maybe I can use the screen instead. Yeah. Oh, here we go. Okay, looking at the wrong screen, I guess. Okay, here we go. So there's the frequency response of my thing. All right. There I did an AC analysis. See, we have frequency, and you can't really see that now. That's weird. That is so weird. So I can alter what we're looking at, but I can't point to it at the same time. Okay.
It's there, it's faint.
It's very faint, yes. Sorry about that.
Colors, it can stand out. I don't know if you can.
No, I can't. I don't know if I can do anything about that now. It's all pre-recorded. But this is I put large noise signals into the loop here. We got one noise in the ground, talking about a ground noise. The ground at the source of the signal is often at a different potential than the ground at the destination, and so you get circulating. You get a voltage difference. You get between the source and where you need the signal. Then you also get pickup in the wires. Wires are known to pick up magnetic fields. That's a Faraday's law, changing magnetic field will induce a voltage in a wire, and that gets picked up as noise in an audio, can be picked up as noise in an audio system. So this system here, so I put a combination of noises here, and they all go away. I can look at that for the. I guess that's the. Let's see. Here we can see they all went away here. I think maybe. Yeah, there we are. So well, let's. There we are. So that's the noise that was left over. With 1 volt of ground noise differential, 1 volt of induced voltage in the wires, and we ending up with, in this particular circuit, nanovolts in the of noise in the actual signal delivered. So it's as good as anything else. The input signal is a let's see, show a picture of that. There's the input. I think that's the input signal, right? And then we have the noises. I put the input signal at 1 kilohertz. I had the noises at 6 and 7 kilohertz, so that they would interfere with each other, and you can see how ugly that looked. Yeah. And then it goes all away, and we end up with what's essentially a mixture of those two sources of noise at various tiny levels. Yeah. Let's see. So anyway, that's so I demonstrated that circuit with LTSpice and can prove analytically that it works. When the Colpitts oscillator is an interesting thing. I mean, everybody knows what an oscillator is, right? Okay, it's been around for 100 years, and the most important thing in an oscillator is the stability of the frequency. I mean, probably the principal most important thing. I mean, other things that are important too, but so it's easy to build an oscillator. It's very easy to build a Colpitts oscillator, small number of parts, but testing it in temperature is another issue. You know, arranging for a temperature chamber or some method of changing the temperature and running tests on it can take a lot of time. But you can get an idea whether something will work correctly or not, or work well enough with LTSpice. So let's say here.
Actually, the most reliable way to make an oscillator is to try to build an amplifier.
Well, that's the problem with electronics, isn't it? I say, so every time I try to build an amplifier, I get an oscillator.
There you go.
And every time I build an oscillator, I get an amplifier.
Exactly.
I don't know why it's always that way. That's probably the original.
I couldn't just copy that in there.
It's true. It's so true. Let's see. So I got this. That's just the standard LTSpice background.
Oh, okay.
So here I am building a version of a Colpitts oscillator, and oh, is that what that is? Yes, right. So I put together a model here, and I'm did it in stop motion here. So we can so we can see now one of the nice things about this is you can, once I've built it on LTSpice, I can interrogate every signal. I can see what the currents are doing as a function of time. I can see what the voltages are doing. I can see how good or bad so you can see here the transistor is kicking the resonant tank circuit. You know, the resonant tank circuit, the resonance of the inductance and the capacitance. It's giving us the oscillation, and the transistor is kicking that like just like a pendulum clock has a little kicker that kicks the pendulum. Some idea here, and we get a signal. The question is not so much how it works, because we know it does. It's been working for 100 years, but how does it perform? So we used a high frequency transistor here, an NVTH10, which is part of the standard library in LTSpice, and move on to some of the testing. What's that?
Q3 was the purpose of
Q3? Let's see here. Go back. Let's look at Q3. Can I see Q3 here? Yeah, Q3 is just to provide compensation for Q2 because Q2 has a base and emitter junction that's a function of temperature, and you want to make sure it's always biased to a more or less constant current. So that's basically a current mirror to make a constant current that doesn't change too much, hopefully, in temperature, and that supplies the pull down for the amplifier for Q1, which is the amplifier that's oscillating. Anyway, in LTSpice, you can very accurately measure the frequency. It's very nice. Just have to set up measure commands, and you can set up a measure command to pick off a certain voltage on the sine wave, and then count and have LTSpice actually count how many times the signal passes that threshold, and then you can report that. You can even do a little math to get the kind of units that you really want. And doing that, but then you can also vary the parameters. You can also vary the temperature. So I did that here. I varied the temperature, and then you can get, when you get look at the error log from the output of the LTSpice, it can show you all the measurements it made. And here I have it set up to do. Anyway, and then not only can you get a printout of all the measurements that were made as a function, in this case, temperature, a lot faster than you could ever do it with a temperature chamber and waiting for your circuit to warm up or cool down. And then by just a key click on the mouse, more or less, you can get a graph of temperature versus the oscillation frequency. What I did here. So that's not too bad. I show how I can graphically, using LTSpice's graphical interface, quickly measure how much change in frequency that is. And I have that here somewhere. So it makes it real quick and easy to tell just how good that was.
transistor from a different company.
You could do that easily. You could substitute a transistor. It can take just moments, and it's a lot easier than waiting to order a new transistor and soldering it in. You can just
in the database directly.
you can add them. You can add it. You can add them yourself. I've added quite a number. You can go online and get Spice models that not necessarily made for LTSpice, but that involve the Spice parameters that LTSpice understands, and you can plug them in and try them. So there's a lot of transistors out there, but they give you a really large database of transistors that come with LTSpice. And I'd say that most everything you need is there for the most part.
Does LTSpice support tubes?
They're not really. There's no. I have to admit, I've been trying to use LTSpice for tubes, but the models aren't that good. Nobody really cares about making a nice tube model, making a good tube model. But there are tube models available. People have done them, and there are primitive symbols that come with LTSpice for tube. But LTSpice itself doesn't provide a model. They provide a picture you can use to add a model to, so you have the graphical. You can engage your graphical user interface. Here I graphed here with that Colpitts oscillator. Here I graphed the voltage of the signal, because as temperature changes, the amplitude of the signal will change, and then that changes. You can see how that corresponds. As temperature gets higher, the signal gets smaller. The signal gets larger, right? The signal is on top, I think. And then as the temperature gets higher, the frequency gets lower. So there's a change there. I was hoping to find where I've actually measured the change. No,
Did you have to add parasitics to the interrupter to get it to self-oscillate to meet the housing criteria?
No, I didn't. No, I didn't.
Because I've tried to use the LTSpice sometimes to model self-resonant transformers, and you end up with convergence issues.
Yes, that's true. I've had that problem myself.
How do you avoid those convergence issues? Add the required parasitics to get it to naturally oscillate.
Well, I think LTSpice has a function internally where you can add parasitics automatically to everything. And you can change the value of that parameter, I
Do you have
believe.
a separate library that you load?
No, it's just one of the functions, one of the settings, Another solution to that kind of problem is to kick the tank with a little pulse circuit. So I'll make a little
Square wave pulse.
square wave pulse to get it started. Yeah, I've done that many times. In fact, more times than I'd like to admit. But in this particular case, it didn't need it. Okay, but you're right. Sometimes it has trouble starting up. These things have trouble starting up. Okay, well, so let's go to the next thing here. I don't think this is not worth the effort here. This was something else I did as a young man. I was playing with model rockets. And I did some interesting things with that, but I don't think we have time for all of that here. But my point in that was it is a simple application of LTSpice to a quasi-digital circuit. This is the 555 timer. It's a circuit that's been around for a long time. There is a model of it in LTSpice that comes with it in the miscellaneous category, and but it's got comparators. It's got a gate, and it is quasi analog. We call that analog and digital. But the thing I want to really talk about is let's see here. This is okay. That's another way of doing using gates to do the. Here I have a circuit that's using gates to do the same thing a 555 does. Just to show. Here we can use digital circuits, but we're using them in an analog circuit way. So we're modeling both the digital circuit and its analog behavior, and we're making something out of that. But the point here is that LTSpice can be used for digital as well as analog, and one of the more interesting things I came across recently, was a friend of mine, Scott Marshall, who I think is actually here. Yeah, there he is, that's right. Who has a real interest in home theater and audio systems in home theaters, found a patent that was used in the day to produce the sound effect in the 1974 disaster film Earthquake. What it did is it made a little circuit. Half of it was digital to create a pseudo random number generator to make the to make a white noise that he then filtered to produce the earthquake sound effect. But their movie projectors couldn't play back frequencies that low. So what they did is they made a generator board that they installed in all the movie theaters, and it was coordinated in just the right way. There were signals on the film that would allow them to coordinate the playing of that sound effect, and they did that. So we looked at the patent. Here, there's the poster, and the patent for the surround system that Universal Studios developed, and there's the circuit that generated the earthquake noise. So my friend has a home theater. He wants to show the movie Earthquake. And so to do it right, you need the earthquake, the original earthquake sound effect generator. And but when we looked at this, there was a mistake. It looks like there was a mistake in there. I don't know if you can see that well, but the original patent is doing something funny with that Q1. We couldn't figure out what that was. But with LTSpice, I was able to get an idea, and so we found out that line was mistakenly shown as making contact with the voltage supply of the CD4011. See there? So they put a dot. They mistakenly put a dot there. But other than that, I was able to simulate the circuit. And so here we have a good example of, so there's the circuit simulation here. I did. Let's see, zoom ahead a little bit here. Running the simulation there. See the randomness of it all. That's including, so it's digital circuitry generating a random pattern of bits. And then you have, this is the interesting, there's an interesting thing here. LTSpice allows you to actually save all the samples it takes into a WAV file. Okay, so we've taken all these samples that would be normally going out to a theater, and total simulation, I got a WAV here. And let's see. And this is what it sounds like. Hope it works. Is there? I imagine they played it a little louder than that in the theater, but
With much lower frequency drivers.
oh yeah, right. That's true. Right. Exactly. So I'm sure. So my friend actually built it after we verified that it worked. So he was in, and this is how he built it. Actually, that was featured in another talk here today. That Jonathan Allen did this morning. But this is, and he actually built it. And he did actually use it to augment the showing of the film Earthquake. And this is that. This is a video of him actually using it to showcase the Earthquake movie. Yeah. I thought that was cute. Right. Another complicated analog digital circuit that I was involved with, which I patented, is a frequency to voltage converter, which has some interesting characteristics. Here's a perfectly linear frequency to voltage converter. It uses some radio frequency technology, but it's relatively simple. But it's a mixed. It uses analog electronics in the front end. It uses digital processing, and then it does some simple analog filter in the output. But and it actually digitally amplifies analog signals which are in the time domain. So the analog is sort of converted to, it's actually, the frequency is converted to time delay analog. Time delay analog is actually amplified by the digital circuitry. And I should say quasi-digital circuitry. It's the combination of a mixer and digital counting circuits. And it develops a perfectly linear voltage output as a function of frequency. Here's this is my LTSpice simulation of it. So you've got a digital logic circuit here, which is concerned with just operating some analog switches to sample signals at the right time. And basically, it's about averaging and about um, determining how long the circuit sits in each state. And then we have a simple. In any case, there's the analog part of this is just an averaging circuit. It's just a filter, just a low pass filter. The digital part of this amplifies the difference in frequency between 2 points and gives you. So here I did a simulation, and I made it kind of interested in applying this to FM demodulation. So I have a frequency modulation of 80 kilohertz. I'm doing this with a broadcast band carrier frequency, like here I did it with a 10.7 megahertz intermediate frequency, which is what you typically encounter. And then so if we run the simulation, we get here. We vary the frequency of input. We get these it's kind of pretty. You get every. So I incremented the frequency a little bit every simulation run. So LTSpice is able to log all that information, all those measure the RMS of every one of these outputs of each case. To measure the RMS signal level of each case for each frequency, and make a report about that, and then it's able to. I can graph that. Here I graph that. You can see it's a very straight line. So I superimposed on that. So I drew a line with PowerPoint to show just how linear that is. So there's a. So here whole idea here was to show how I could take a combination of digital and analog circuits, combine them together, and do something useful. So those are the main things I wanted to showcase, give you guys an idea of the scope of what you can do with LTSpice. For audio design, for audio electronics, the Fourier feature, the Four feature, which is short for Fourier, is very useful for measuring distortion. For oscillators, you can do triggered measurements that are very good for accurately measuring the frequency of an oscillator that it's simulating. And then, as you saw, we developed temperature versus frequency of oscillation curves. So it's got a lot of features like that are helpful to designing electronics. This is just a small number of small sampling of the things it can do, but it can do them. Give you some real insight into circuits, helps you to see how the circuit operates under different conditions quickly, different parts with different parts and with different operating conditions. One of the things I did with my headphone amplifier, which I wasn't able to show before, you can very quickly measure how much power a device is actually consuming, which is interesting. Now that I know how to do this, I go back to the headphone amplifier here. I go back to the headphone amplifier, eventually get there. Here. There you go. And you want to see quickly how much power this chip is able to deliver. So we can do that. Let's see here. We can get right there. Where is that happening here? There somewhere. There. No, we just had it. Where's that one? There's a frequency response. There's the that was the distortion levels. And there we get power right there. So all I did is put my cursor over the load resistor, which is simulating the headphone, and it's showing me 341 milliwatts. And I also did. You can also just put the cursor over the part and quickly measure how much it sums up all the power consumed and all the currents and all the voltages and all the pins, and instantly gives you a tells you how much power the part is dissipating. It's something you can never do with a breadboard. So to get an idea of what kind of heating the devices undergoing is very, very good for that. We'll show that here if I can find it. Let's see. Let's see here.
Can I ask the question about EWB for the ultimates?
What's that?
Can I ask the question about EWB?
EWB? What's that?
Electronic reference.
Oh, yeah, that's a similar. It's not unlike Spice. Yeah, I've never really used it.
I haven't used it in years, but when I was a beginner, it's around. But I tried to make a simple circuit, a battery, like a 1 amp fuse and a 10 amp light bulb, and it would go to fun. It would go come with anything.
Oh, yeah.
I could never get the circuit to work. Could you have a reference for it? I don't know.
It could be. That's a common mistake with Spice simulations. That's right. Everything has to have a reference. That's a or you have to have op amp. If you don't have a reference, there has to be some pathway to ground somewhere, or otherwise the system can't find solution.
The machine knows it, but doesn't tell you. That's the point.
I guess the software engineers figured you knew things like that, you know. Yeah.
If you want to make an isolation, you have to add. You don't move around with reference, it's going to take all exploding.
Right. I had to go to some special lengths to make a model for a floating amplifier. The idea is my transformer, my synthetic transformer isolation technology involves operating the op amps on floating power supplies compared to the destination ground reference or whatever ground reference. And to model that is a real trick, because any pathway back to ground, and you have to have pathways back to ground, or else LTSpice is unstable, won't find solutions. It won't work. So I had to make my own op amp models, which could work in what is virtual isolation. So that was a problem for me, because I tried to sell the technology. People would try to put it up on on Spice, and it wouldn't work. And so they came to the conclusion that the product doesn't work. The technology doesn't work. It's all smoke and mirrors. And but it did work, and it's quite pleased with that system. Any other questions? I guess.
Pretty good, but I'm not sure if you're asking correctly. So I work on airplane radios in Hawaii. People are always asking me to make microphone circuits for them. They want to spend money to a car. So I couldn't figure out, I was mostly transistor. I couldn't figure out how to get a small microvolt signal from a microphone and amplifier. I get contracted it out. With an op-amp, it's so easy, but I don't understand how you bypass it with the DC power supply. How are you bypassing the point of exchange limit, the bias limit without using a capacitor? Is it possible? Or?
Yeah, you use resistors to provide a bias that sends the transistor into conduction. Actually, I can show you actually my.
You have preamp.
Here's.
And I wasn't qualified to be making. I was just.
No.
But I don't understand how you amplify with a DC power supply and micro battery.
Well, here's my.
Microvolt signal. You got your biases. Or microphone itself.
Yeah.
Then you have the signal.
Well, here's my headphone amplifier that I did with discrete transistors. Here's my. It's got a gain of 20. What happened? Did I just? Was there a minute ago? Okay, let's try this again. There we go. There it is.
You gotta calculate the load line.
So you see here.
Transistor.
So there's a transistor. Now this has a 20 times gain, this thing, and it can drive a headphone amplifier. It can drive a headphone. It can drive a headphone. 32 ohms, very nicely.
So C3 AC coupling to the bias.
Right. This blocks the DC, so the DC can develop for the transistor, but there's no DC on the microphone because the DC would ruin the microphone's performance. So we have a capacitor blocking the DC. So the AC gets through, and then we have two resistors here which provide a biasing for that transistor. So the transistor is biased in an on condition; it's always on. So the 0.6 volts is not a problem because you provide voltages that make the transistor turn on all the time. Transistor is just on all the time.
So Q1 is bias class A, and then he's using a emitter follower to really drive the output in Q2, and Q3 is compositor.
Right. So this one was, I remember we had like 0.06% distortion with the IC chip. This one here, when you do the distortion measurement, came out to be, well, that was after I overloaded it. Let's see here. Would be right in there. See, I overloaded it. I put more than 125 millivolt signal in there. And then, so this one's 0.86%. So my class A design ended up 0.86% distortion. And that little 8-pin dual inline power amplified chip, the LM386, did 10 times better. And a lot easier, by the way, with one 8-pin chip. So I was persuaded to from now on use an LM386 for any kind of little audio driver. But like I said, LTSpice can help you get answers to a lot of questions, help you verify, and help you make sure that your circuit's going to behave and operate with the kind of specifications you want. Faster than you can get the organize the equipment and organize whatever it takes to make the measurements, even for simple circuits. But it's capable of doing quite a bit, as we showed, as I did illustrate. Mixing analog and digital can do both. A company to look at, to keep your eye on, is Qorvo. Qorvo hired David Engelhardt, who actually did this, who made this LTSpice work so well for linear technology. They hired him to do the magic for their company, and they're involved with much higher speed things, naturally, and also it makes sense to try to incorporate more digital in LTSpice. So the idea is, or into Spice. So the idea is, let's allow for specifying devices with hardware description language, like Verilog. I don't know if any of you know what that is, but hardware description language, so you can you can get some very high-speed functions that way, and using and specify them in the simulator. So you get exactly the function of that hardware. You can actually write a C program in Corvo now, and actually run a C program to make a device that does whatever a C program can do. So you have that embedded, and you can tell in advance whether your little microprocessor that's running a C program can do the thing you want the way you want to do it. I think it's interesting that simulator, that LTSpice running that Corvo is now distributing. They say that it can run the C program for a microprocessor emulation faster than the microprocessor can. So at some point, it's more than an emulator almost.
That sounds like those people be averages.
Oh yeah, right. I see. Well, the thing is, it's a company to watch because they're doing all the right things with LTSpice, and in terms of the integration of analog and even advanced digital, even very advanced digital, they're doing it there. I understand that I don't know that they have a version for the Mac, but I understand that they're working on one for Unix. But anyway, it's one to watch, and since Michael Egelhart did it, I'm sure it's compatible with all the Spice models that work under LTSpice, and that unfortunately it's not compatible with the schematic files. In LTSpice, they're called .asc files, and unfortunately Corvo doesn't work with .asc files. But it's apparently he solved some problems with convergence. Apparently the new Corvo engine or solver is much less prone to get hung up. It's much faster in simulation. So it's one to look at. It's one to keep your eye on, especially if you're doing extensive digital designs or incorporating essential digital circuit blocks.
Do you